All right. Success. This has got to be the most finicky projector I've ever worked with. All right, so last time, welcome to passing through early drop. Congratulations, everybody. You are now officially in the class. Hopefully, you better make sure that any of your friends who might have thought they were still on the wait list realize that there was no wait list and everybody that didn't drop got in. So, anyway, all right. So last time we started talking about networking and services to give you a flavor for that style of programming. And if you remember, for communication over IP, we had a couple of different namespaces. We had the host namespace, which of course resolves via DNS to something that looks like this, which is, in the case of IPv4, it's 4 8-bit numbers, and in the case of IPv6, it's a 128-bit number. And that's the actual address that's used by network routers. And then the other piece of namespace is the port. And the port is a 16-bit number, and some of these numbers have explicit meanings. So all of the numbers from 0 to 1023 are actually predefined system ports. It used to be that security was gotten by putting only secure things on those ports and so on. That's a little different these days, but a lot of the things you're used to thinking about, like the web, is what? Port 80 or port 443. If you're sending messages, it's port 25. So a lot of the standard services you're used to are there. And then registered ports have a lot of other more extended services. And then last but not least is this range of dynamic or private ports. And does anybody remember what those are good for? What are the dynamic ones good for? Why do we even bother mentioning them? Anybody remember? Yeah. Okay. What about sockets? Good. So they're about uniqueness. So remember, we talked about how networking connections have a 5 tuple that represents a unique connection, 2 IP addresses, 2 ports, and a protocol. And these ports in the high range here are actually very important on the client side to make sure that your connections are all unique. And I'll remind you of that a little bit again. But using sockets, which is something that you're going to do plenty of in this class, on the server, you have to actually set up a server socket and execute a listen system call. And that server socket is not for communication, but rather it is primarily for waiting for communication. Every other socket represents an endpoint. So any connection that's actually used for communication has 2 sockets, 1 at either end. The server socket is it's there to help you set up a connection. And I'll show you that in a picture, which I showed last time as well. And once you do listen on that server socket, then you can do multiple accepts as clients come in. And each successful accept gives you a new socket that can be part of the connection. All right? And on the client, it's simpler. You just create the socket that says which host and port you want to connect to. For instance, for TCP, you perform a connect, and assuming the server is up and everything is working out well, that connect will be successful, hopefully, and then you'll have a connection. Okay? And this was a picture that I showed you last time to kind of give you that flavor. So if you notice, that server socket in the upper right-hand corner, that is something that a service, like a web server, sets up a server socket. It says, here's my IP address, and I want to bind to port 80, for instance. If you have Apache, that might happen. And all that socket does is it waits for that connection from the client on the left, comes in and says, hi, I'd like to talk to port 80. And the server socket then makes that yellow connection between the 2 green sockets. So it makes a brand new green socket on that right side and sets up that connection. And now that yellow channel is a unique channel over the network that the client and the server can talk to each other with. Okay? Are there any questions on that? Yeah, question.
If there are multiple connections, multiple yellow lines, is that represented with multiple physical lines, or is it can it be all done with one physical line?
That's a good question. So if there are multiple clients connecting to the same server, does each yellow connection have to be a different physical wire, right? No. All that has to happen is each connection is uniquely identified by 5 items. The 2 IP addresses on either side, the 2 ports on either side, and whether you're doing, for instance, TCP or UDP. That's the protocol. And so, in fact, if you have 1,000 clients all talking to the same web server, you know that one end of this connection will be represented by the server address and server port, which is going to be the same for all 1,000 of those yellow arrows. But what distinguishes them is the client-side IP address and port. Okay? Now, you can kind of see a little bit how those dynamic ports come into play. In fact, we're going to walk through the code that I flashed up for you at the end of the lecture last time. But typically a client says, I want to talk to this IP address and port. Get me connected. And the local operating system says, well, let me pick a port that's not in use for you to make sure that that connection's unique. So the local operating system uses one of those dynamic ports to help make those connections unique. So in fact, you could even have a client with a single piece of hardware, meaning one IP address, that has 12 sockets all going to the same other side. And they can all be kept unique because each one on the client side has a unique port. Okay? Everybody parse that? So how many protocols are there? So I told you about TCP, UDP. Did anybody have any idea? What are some other ones? Anybody heard of any others? Anybody know? How do you sometimes figure out whether a host is alive? What do you execute? Ping. What protocol is that? ICMP. Are there any other ones you know about? Yeah. Yep. There's a lot of protocol. Well, SMTP is actually typically over a transport of UDP or TCP, but there's up to 8 bits worth of protocols, but the 3 you just named are pretty much the very common ones there. In the early days, there were a lot more protocols, but there are a number that are still there, and they tend to be things that don't look like standard connections, but are sort of unique application-specific ones. But anyway, so as long as you know about those 3, you're kind of in good shape. These here are often all over TCP, so these are the ports. These are different from the protocol. So port and protocol are different things, okay? Protocol is UDP, TCP, ICMP. Those are good to remember. Okay, so if you remember, at the very end, we're talking through an example where we put up a web server-like thing, and clients were connecting to it. Everybody remember that little thing? We started out with no protection, then we added in a separate process per connection, and then we allowed there to be many connections going on simultaneously. And so that was this last version. And the first thing that's going to happen on a system like this is the server side is going to create a server socket. That's that gray thing that was in the upper right-hand corner of the diagram I showed you. And it's purely for listening to incoming connections. Okay, so we bind it to the address, which is a combination of host and port. And then we listen on it. That's a system call. And that listen, okay, is basically tells it to set up a queue and wait for incoming connections. And then when we come back from listen, we do a system call called accept. And that accept is a blocking protocol where it just waits until the next connection comes in. Okay, that's why I've got this little dotted blue line that really represents we went into the kernel and we went to sleep and we waited. Okay. By the way, something that I noticed when I was watching various queries from people recently is somebody somehow managed to create the word block-ing, and they were thinking that that was somehow putting things together in a block. No, the word blocking means put the process to sleep because you're waiting. Okay? Just keep that terminology in mind. We're going to talk a lot about synchronization and blocking and so on in a week or so. But when I say the word blocking here, I'm not talking about putting things into a block. I'm talking about putting the thing to sleep until you're ready. Okay? Now on the client, so this server now is ready to go. So on the client side, we create the socket and we connect it to the server. So that's a connect system call where we say, here's the host and port I want to connect to, and that's got to match the host and port the server is sleeping on. Okay? And that connect is does several things. So how many protocols or how many numbers make a unique connection? 5. Okay? We know 2 of them, host, port. Okay? What are the other 3? Well, this is the server host port. So the only thing I'm calling host and port here is actually the server side host and port. So the client IP address, the client port, and the client protocol is not on this diagram. Why? Well, typically when you do a connect, you kind of say, well, I want to connect, use my IP address, and pick a port for me. So that you don't actually have to tell it what your IP address is and what port you want, because that's part of the semantics of connect. And the other thing is when you make a socket, you sort of tell it, what kind of socket is this? Is this for TCP? Is it for UDP, etc.? And so a lot of that's implicit. So this idea of connecting to the remote host and port is exactly what I've got there, and those other parts that make it a 5-tuple is hidden under the API. I just wanted to make sure that was clear to everybody, because when you start programming this, it's going to get very annoying the first couple times you try to get things working. Okay? So what happened here was the connect reached out to the queue on listen, which reached back and connected these 2 green sockets. Remember, we had those together, and returned from accept. So if you go back here, isn't animation wonderful? Look, when I did connect, it sent a packet out. There was an established connection that was set up, and what came out of that is the system call for accept returned. It had been sleeping all this time. It now returned and said, here's your socket. And meanwhile, that socket that we constructed in the client is now connected. So once we get to this point, now we can just communicate. You know? And that's great to go. Now, remember the protection portion? Now we pulled in fork. How many people think fork is their favorite system call so far? How many people think it's the weirdest system call you've seen so far? Okay, it's a little weird, right? So what we also talked about was in order to allow parallelism and protection, the connection socket we forked at that point into a child and a parent process. The parent just went ahead and closed the connection socket, which we just generated, and then went back to sleep and accept. Can somebody explain to me why I close the connection socket and then go back to accept? What does that mean? Yes?
Because the child is already running an initial copy of the current connection you don't need to open, and you want to close it so they can go back and accept new incoming connections.
Great. So when we fork, the child and the parent have the copies of not just all of their memory, but all of their open connections. So after that fork, both the parent and the child had a duplicated connection socket. The parent doesn't need that one because the child's going to do all the stuff that represents the service, right? So we close it out. Okay? Questions? So now what happens? Well, the child is a separate process, which is protected. So it closes the listen socket. Why is that? Yes?
Because that's the parent's job?
Yeah. The parent's doing the listening. The child doesn't need to know what that socket is. Okay? Good. But it still has the connection socket. And then, it does a read request. Well, remember, reads are blocking. Okay, so we wait. Meanwhile, back at the fort, the client sends its request. Gets to the read request wakes up. The server socket does something with it, sends a response back, and then we can wash and repeat many times. That's a communication. And then when we're done, client might close its socket. That would cause the child over here to close its socket, or you can close either side, and we're done. Okay? Notice that this server that we've got set up here basically just keeps accepting forever. There might be some circumstances under which it's going to just exit, and it does. Okay? All right. Any questions on that code? That's the version 3 of the code we walked through, which kind of represents what actually happened in the early days of web servers. Yes? Question? Any reason we can't do what with the connection socket? Oh, I see. Why not fork first and accept? Well, because you want to fork first and then do the accept inside here. Well, the problem with that is that potentially you don't know how many connections you're going to have, so you don't want to generate an arbitrary number of child processes until you actually know you need one. So that's one thing. And so in some sense, the idea of accepting a connection is something the server's doing here. And you could imagine, in fact, more interesting authentication that went on where not every connection's accepted. Maybe it validates that it's only from the local subnet and certain things are true about it, whatever, before it accepts it. And so that's the kind of thing you might imagine putting into the parent in that case. Okay? Any other questions? So when you look at code, here's the protocol. It was version 3, but notice there's the listen, which basically says, here's the maximum number of things I'm going to queue before I start dropping queries. Here's the socket. You will have set that up early. And then we go into an infinite loop while 1. And this accept system call goes to sleep until connections come in. So if nobody knows about your server and nobody's connecting to it, the server's never going to exit that accept call. The only reason you'd ever come out of accept there is if there is a new connection. Okay, and when that new connection comes up, there is a socket associated with it. And it's like, oh, good, we have a new connection. So we do our fork. Here on the parent side, how do I know it's the parent? Because the CP ID is not 0, right? So I know it's parent. I close the connection socket because I don't care. Why does this code loop back to do another accept? Okay, yeah, not only while 1, but notice, here's an if. We go out this other arm, and now we're back to the while, okay? So I had a couple of questions in my office hours, which were kind of interesting. People were asking about exec. When you do a fork and the child does exec, what do you put after the exec? You say if, CP ID is 0, exec, and then what do you put after the exec? Yeah, only check if it fails, because if it succeeded, there's no arm of that if left because it wiped everything out and put the new program in there. So exec is a little weird. Okay, and we'll talk more about that later, but that we don't exec here. On the child side, we close the listen socket, and then we run a server with that socket. We can do whatever we want, however long, and then eventually we close. And then notice here we actually execute exit. So this actually kills off the child at that point. The child's no longer executing because we did exit. And where does that exit code go? Because we exited, the child process disappears from the face of the earth. Where's the exit call go? Yes?
It gets passed to the kernel and then passed back to the parent process.
And how does it get passed back to the parent process? Oh, it does a wait. Good. You know what happens between the exit and the wait? And then what's the kernel do with it? It's a number 5. That's cute. Yeah? Stores it. So I haven't... Yeah, go ahead. So I wouldn't necessarily expect you guys to know this yet, but there's process control blocks, which we will talk about shortly. The exit code is stored in there, and the process is no longer running, but it's kept around until the parent can ask for it, the return code through wait. We call that a zombie process. Okay, so you can end up with the zombie apocalypse here if nobody ever executes wait, and you have a lot of processes that just fork and exit. But fortunately, if the parent is dead, then the parent's parent will be able to wait and so on. So we don't actually get too many zombie apocalypses unless something's very bad. So if you look at what happens as a little more detail here. So how do we get the server address? So remember, the server address goes to the listening socket, and we have this structure called a sock adder in for internet, and it has a bunch of interesting fields like what family are you in and so on, what port, what address. Okay, and notice the address is a structure, so we're not necessarily restricting ourselves to an internet address. It could be address of some other protocol. All right, and so for instance, in the case of a regular internet style server, what happens is we have a sock adder in that we have generated. I didn't put that code here, but we zero it all out, and then we make the various fields be what we want. So this SYN family says it's an internet protocol. In-adder any says that any address that the local machine supports can be bound to, and then the port is the port number of interest. So what's a little funny about this is why in-adder any? Well, can anybody guess why we, on the server side, say that we could have any IP address that we want? Seems a little weird, right? Why not just put the IP address? I can think of at least, go ahead. Okay, so first of all, the code doesn't have to know what the IP address is. That's good. The second thing's a little more subtle, but it's possible to have a bunch of different network cards inside of the same server, and they can all have different IP addresses. And this particular code says whatever hardware address you're coming in on, put a server on it, kind of. So, all right. So it's a simple form. It's the internet protocol accepting any connections on the specified port, so to any IP address I happen to support. And in network byte ordering, that's what this H2NS means. So basically, the other weird thing you're going to have to start dealing with is anytime you deal with numbers, integers like ports or IP addresses or whatever that are going over the network, you have to put them in network byte order. Okay, so you talked about big and little endian in 61C. Well, big and little endian are a real thing, and so the way that the network deals with it is basically you have to put them in a network order. Does anybody know what the network order is? Is it big or little endian? Big endian. Yeah. Good. At least you guys are watching. So for instance, this code for getting the server addressed, we do get host by name to get the actual server in a host entry form, and then we go ahead and we extract the information we need to out of it. Like here we're copying the address, and we say it's INET and so on. And this is how the client, for instance, could also get an address by host name. So, okay, so you should do man. Man is your friend. Have I said that before? Okay. So here we're actually zeroing out the structure. We're setting up network information, copying the server addresses in, and so on. And so this is, for instance, how the client can figure out how to connect with the remote server. So potentially, for instance, I don't know, maybe Cal or Berkeley.edu or whatever would be the host name. That would give you the server's address of that website you're trying to connect to. And this, we're setting things up in order to say what the server is we want to connect to. And so this is how the client gets the server's address. Okay, and so on. So questions? I just wanted you to at least see this sort of thing in class once and hear network byte order and know that you can look this kind of code up. Okay? Good? All right. So traditional Unix process has one thread and one address space. And in the past, that was what a process was. It was a single-threaded process. And nowadays, since we know that we can have many threads per process, this is often called a heavyweight process. I like to talk about it as it's like the prototype of what a process is, and then adding a few extra threads is not a big deal usually, not today. But there's two parts. This is just reminding you the sequential program execution part is the thread, it's the active part, and the protection part is the passive part. Protection part is what we got out of our branch and bound, or our various protections that we put together, right? We talked about memory protection of various sorts. That's the address space. It's also the I/O state, like the file system and so on. So that's the protection aspect that the process has. The execution portion is the thread aspect, okay? And it's the state of the CPU registers and so on. Today, for the rest of the lecture, we're going to talk mostly about this active part and multiplexing a little bit more. So we're going to circle back to what we talked about in the third lecture or whatever, but do a more interesting detail, okay? So how do we multiplex processes together? Well, there's a process control block, which has the state and what's its process ID and what's its program counter and register values and memory limits and what files are there. So if you have a bunch of open file descriptors, they'll be stored in the process control block and so on. And in a single hardware execution unit, there's only one PCB active at a time, but we multiplex through them. If you have 12 cores, you know there may be at least 12 PCBs that are potentially active, and if they have hyperthreads, maybe there are 2 hyperthreads per core, there could be 24 PCBs active at once. Okay, but this represents kind of the single execution context and its protection state. We're going to give CPU time out to different processes. That's scheduling, and only one process is running at a time on that CPU, and give more time to important processes. So this idea of scheduling is now going to be interesting. We have to decide which processes get which parts of the CPU. And the other thing that we're going to do as a part of the protection is there's a form of protection scheduling as well, which is giving pieces of resources to different processes correctly. So controlled access to non-CPU resources, controlled access to the proper memory, etc. Okay? And if you think about it, if you switch from process A to process B and back again, you got to switch out the memory state of process A and put in the memory state of process B and vice versa in order to keep the protection correct. Okay. Good. So here's a good example. So for the remainder of the next several lectures, just assume that we have no multi-core and only one thread per core. But for instance here, process 0 is running, and all of a sudden we get an interrupt or a system call. We save all our state into the process control block for process 0. We go over and we start executing process 1 after we reload the state for process 1. So save process 0, reload process 1, start executing for a little while, go back, save process 1, reload process 0, and continue. And as a result, by going back and forth, saving and restoring the process control blocks, we basically multiplex. Okay, and if you remember back to my diagrams early in the class where we looked at, cyan, fuchsia, yellow, alternating between them, this is that idea here, but now we're taking the whole process control blocks back into play. Okay? Now, what's interesting here is this overhead sets sort of a minimal practical switching time. So if you look at the amount of time it takes to save and restore the register states, and you try to switch faster than that, then basically you're going to be getting no real work done and doing nothing but switching. Okay, what do we call that typically? Thrashing. Not deadlock, because they're potentially making a little bit of forward progress, probably closer to live lock. All right? But, yeah, thrashing. Okay. And so now that we have an idea of this processes and the process control block, we can start talking about the life cycle of an actual process. So as a process executes, it goes through a series of states. So new is a creation state where it's not ready to run yet. It gets admitted to the system and put on the ready queue. This is a situation where the process control block is scheduled to run, but it's not running. And there may be a lot of those, okay? And at some point, we switch it in so it runs for a little while, so now it's running. Okay, and then what happens? Well, there might be an interrupt which puts us back on the ready queue and so on. This is kind of the normal mode, back and forth. Okay, so if you look at it from the standpoint of a process, it's going through this ready queue, running, ready queue, running, ready queue, running. And when you do a PS, how many people have done PS on their machines, right? And your VMs, you look and you see the set of all processes that are running. Are they actually running? Not only one of them at any given time is actually running. The rest of them are on the ready queue. Okay? And in fact, that statistic of how much CPU is given as a percentage, which is kind of the percentage of the ready queue that it's taking at any given time. So what happens here if we're running and all of a sudden we do an I.O. event? Okay, so maybe we do maybe we actually try to read a file. Okay, so you do a read system call, and at that point, we're no longer running because we're in the kernel and we're maybe waiting for the disk. Okay, so a waiting state is all of the processes that are waiting on external events, like the disk drivers, they're waiting for network, they're waiting for any other I.O. Okay, and then of course eventually the I.O. completes, they get put back on the ready queue and they get to run again. Okay? All right. And then finally, we exit, and what's interesting is the process is finished execution. You're in the terminated state. It doesn't mean that it's gone. But possibly that PCB has to sit around with its exit code long enough for the parent to ask it for its exit code. And so those process control blocks can sit in that terminated state for a while, okay, as zombies. So that's why we even talk about this state. It might seem kind of silly to say, well, this process is terminated, but it's because it hasn't had a chance to sort of say what happened to it in the grand scheme. Okay. And so if you look, basically the general scheduling idea here is we go from the ready queue, sometimes we run on the CPU for a while, and then there's a bunch of places that you can end up waiting to do I.O., or your time slice might expire, in which case you go back to the ready queue, or there might be a child fork process here, in which case the child executes and you don't. So if you think about what happens with fork, there's only one thing can run it at once, but now we have two things, right? So one of them has to go on the ready queue. Okay. And so there's many scheduling algorithms which are really about which thing do we take off the ready queue to give to the CPU at any given time and why. Okay? All right. And so the ready queue and various I.O. device queues look kind of like this graphically as well. So the process not running means the PCB is on some scheduler queue. And there's a separate queue for every device or signal or condition, and every queue can have a different scheduling policy. So here's a bunch of queues. The ready queue has things on it, a linked list of PCBs that are ready to run. These are the ones that don't have any outstanding conditions that are preventing them from running. They just have the misfortune of not currently having the CPU. But they will, oftentimes the scheduler will grab things. One example is maybe they grab them in FIFO queue order, let them run for a little while, then put them at the tail of the queue. When we talk about more interesting scheduling, like real-time scheduling or what have you, in that case, then you might take them off in a different order depending on, for instance, which one has an earliest deadline. So there's a real-time scheduler called earliest deadline first. And in that case, you don't take these off in order. You pick the one that's most urgent. Okay. The rest of these things represent PCBs that are sitting on queues waiting for external signals, and there may be a lot of them. And by the way, this the little ground symbol is basically null. Okay. So if you imagine there's an arbitrary number of those wait queues based on how many devices you have, there can be software wait queues. There can be sockets. So for instance, when you go to read from a socket and there's no data there, you get put to sleep on a socket wait queue. Okay? All right. Any questions? Yeah, question.
How is the queue and PCB related to the kernel stack?
So typically when you're put onto a wait queue, you take everything you need with you to be restarted. So if there's a bit of the kernel stack that you need for that, that's packaged up in the PCB. Okay? All right. I'm going to show you more examples of things that might answer that question later in the lecture. Yes?
When you're in the terminated state on the FSM that you showed earlier, is it just the PCB that's not released, or is the memory that process was allocated?
So typically the memory is gone, and it can be put on wait queues directly associated with the parent. There are different ways of implementing this, but you can, the extended resources that you might imagine could be usable by other processes are gone. Really, the main thing there is the exit condition and, a few other things that are kind of managerial information about statistics for running and stuff, but none of the big things, none of the memory, none of that stuff. Good. Question, yeah. Do I think the ground symbol is a good null?
Or is it is it commonly used like that?
I don't know. I thought I'd mix it up for you today. We are in the EECS department, so, All right. Some administrivia. So, wait list closed on Friday, so no more people can get in and no more people can get out. You're all trapped. No, I'm just kidding. So make sure if you have friends who thought that they weren't going to get in and just forgot about the class, I don't know if you know anybody like that, but you should talk to them. Make sure they know that they need to figure out how to drop if they're not taking it. Again, try to look at some of the readings before class. That can help. Group sign-ups are happening this week. So now that we kind of know how many people are in the class, at last look, it was somewhere between like 402, 403. We need to get you in groups. So groups have 4 people, and the deadline is this Friday. So by this Friday, there is a group sign-up. I saw it posted on Piazza. I think it's one of the pinned things from our head TA. Make sure that you take a look at it, and don't miss it, okay? We want 4 people per group. I realize that 4 times X doesn't necessarily equal 403, but we'll see how this goes. Okay? I'm a big fan of new math, so we'll see how this works out. All right. I don't know if they even talk about new math anymore. It was new when it was new, and now it isn't. But anyway, so for this Friday, continue to attend whatever section you want, and starting next week, then we're going to have assigned sections, which that's the TA preference. Also on that Piazza posting about next Tuesday is when you have to say which TAs are your preference, and that's when we then run the algorithm to try to satisfy everybody's preferences. All right, so don't miss these 2 things: group sign up, TA preferences. Okay, how many people are working on homework 1? Good. Okay, how many people are working on homework 2? Hopefully nobody, because we don't have homework 2 yet. Okay. Any questions? Okay. I think also that we may have some way of people who don't have a group and don't know what group to get in. We'll have a way to have stragglers sort of post. Let your TA know if you're in that category. All right, good. Okay, so now let's talk about modern processes with threads. So a thread is the sequential execution stream within the process, which we're now going to kind of, sometimes they call lightweight processes, but this is a very bad terminology because process is really about the combination of threads and execution context, which is threads and address space, okay? And there's no protection between the threads that are within here, okay? Multi-threading is typically a term that means when a single program made up of a number of different concurrent activities. Sometimes it's called multitasking, okay? Why do we separate thread from process? Because the thread is really ideally a part of the process. It's the concurrency element. It's the individual execution thread of control. And it's separate from the protection context like the address space and so on. Okay, and this old school heavyweight process is really a process with one thread. But I'm going to show you an example of how very few processes have one thread anymore. When you're interacting with user interfaces, you got tens of threads easily. Okay, so very few heavyweight processes anymore, except for maybe ones that are running in the kernel. Okay, even those are probably multi-threaded. So here was this picture that I showed you a while back. So here's a single-threaded process. Here's a multi-threaded process. Threads are the concurrent active part. The address spaces are the protection. And they're keeping buggy programs from trashing the system. All right. I realize this sounds repetitive, but I want to make sure we're all on the same page. Were there any questions here? Do you see how every thread has got its own stack, its own registers? Potentially, there's one large part of code shared by all the threads, but the threads are often in different parts of the code. So you start a thread, per different routine, whatever. Yeah, go ahead.
So if multiple threads are blocked on multiple I/O devices in the PCB queue, is there some sort of identifier to tell you which thread you're waiting for?
Yeah, so the PCB has in it thread control blocks, and they can be individually blocked. Yes. There are other interesting ways that you can handle blocking of threads, because you might say, well, I need 3 threads because I need that level of concurrency. Man, when one thread goes to sleep, I'd like to get one back right away. So there are actual ways of doing that, where you keep the number of threads constant, and then you have these threadlets, or whatever you want to call them, put to sleep, also on the process control block. But for now, assume that threads can block, and when they block, they're put on a queue and kept track of by the PCB. Okay. So why have multiple threads per address space? Lots of good reasons, right? You've got concurrency. You're trying to get actual parallelism, or you have one of these represents a control like a button in a windowing system, and maybe it goes to sleep until you press it and then it does something. There's lots of different ways to use threads. Okay, so let's just assume that that's what we want, because it's a very useful modern programming abstraction. So what is the thread state? So this is the state shared by all threads in the processor address space. The content of memory, global variables in the heap, is shared by all threads. The I/O state, all the file descriptors, network connections, etc., are also all shared. So those are process-wide resources. Okay? The private to each thread, or thread control block, are things like CPU registers, execution stack, etc. I'm going to remind you guys in a moment what the stack is. I know it seemed like people knew that last time I asked, but let's just make sure. All right. You've all sort of worked through the stack in GDB, I think, maybe with homework 0 or 1. So what is the stack? So this is parameters, temporary variables, return PCs while procedures are executing, etc. So let's take a look at this shared versus per thread state. So the shared state is heap, global variables, code. Per thread state, each thread control block has stack, registers, metadata, etc. Okay. So let's look at the execution stack. So stare at this piece of C code. This is a little bit simplistic, but notice the A routine has a single input temp. And if temp's less than 2, we call B. Otherwise, we do a printf on temp. Now, that's not a real printf. What's wrong with that printf? Go ahead. Say again? Yeah, it's missing the format string. So this is Kubi's printf for lecture 5, right? What it means is it takes as an argument an integer, and it prints the integer followed by a space. Okay, I could have put the format string in there, but it would have been too tight for the slide. So believe me, I know that that's not printf, but let's pretend it is. Notice that the B routine calls C. The C routine calls A of 2. Okay? So that's the code we're going to trace through. And the first thing we do is we call A of 1. So what happens? Okay, so when we call A of 1, notice that calling of A of 1 means that we have a stack frame that gets set up where the temp variable is set to 1, and the return, what happens on return is actually exit, because when we return from A, in this one instance, we're going to end up back here at exit. Okay, so notice how on the stack we have the return value, and that's going to help us make our procedure calls work. Okay, now in a real modern RISC processor, what actually happens is the return value is kept in a register until you try to call somebody else and then it gets stuffed on the stack. But that's a register calling sequence that will complicate your life in a few slides. Let's just assume for the moment that return value is on the stack here, okay? And so the stack pointer is going to grow down, and what happens here? Well, we work our way through. Is temp less than 2? Yes. So we're going to call B. So B gets called, and now B says that the return value is A plus 2. Okay. What does that mean? Okay, it means that when we come back from B, where do we start executing? Right here. See that? So what's the return value is the point in the code immediately after the point that we just called. Does that follow what everybody imagines that procedure calls are like, right? So the thing about the stack is it's the ultimate kind of keeper of statistics as to how the execution is supposed to go. Now we're going to execute C. Well, C says when we come back, when we return, we're going to return to B plus 1, which really means we're going to return out of B to exit and so on, okay? Good. And so now we call A of 2. So now notice the second time we called A, the temp variable has a different value this time. It's got the value 2. So we're calling, and we're several frames into the stack. We have two different values of temp and executions of A going on simultaneously because we've been pushing our way down the stack. Okay? How many people does this look very familiar to, I hope? Many of you? Good. And so, well, what happens here is temp less than 2 in this instance. No, because it's 2, right? So then we, Kubi's printf, and we end up with output equals 2. Okay, and this is your little prompt there too, so this is our screen. The output 2 is there. Okay? And then what happens? We get to the end of A, and now we're about to do what? Well, we got to return, and where do we return to? Well, we look at the stack, we're going to return to C plus 1, which is right there. Why do we know that? Because A of 2 called us, and when A exits, we return back to where we were, right here, where we're going to now return to the next one up. But I want to make sure everybody understands. If we're at this point, and we go to do a return, we're going to come back to this instruction. So how many people have, if you have any questions, ask now. Because this, yeah, go ahead.
On the previous slide where you showed like all of the things that are shared and distinct, how do you enforce that the stacks like remain distinct when all of your memory operations are going to the same cache?
Okay, that's two good questions. So let's do the first one. Can I remove the word quick? I'm going to remove the word cache from your question, okay? So the first question could be if I have a bunch of threads that are in the same address space, how do I make sure their stacks don't get messed up? They don't cross over to each other or something, okay? And the answer is, when I start, for every thread, I start its stack in a different part of the memory space, and it's going to have its own version of the stack pointer, which is where its stack is. And when I switch to the other thread, I'm going to change the stack pointer, and so it'll keep track of that. So the simple answer is, because I start them out with stacks that are in different parts of the memory space, it works. However, hold your question. However, if you think through this, you might say, well, what if it really screws up and they start popping off the stack, or they do something wrong, and the stack pointer for this thread goes all the way up to here, and it starts messing up with that stack, right? Doesn't work. You get garbage, okay? So that's correct. Because the two threads are sharing the same address space, they can execute in a way that messes each other up. That's the advantage of sharing memory is the disadvantage of sharing memory at the same time, okay? No protection. Now, as far as the cache is concerned, the thing to think about, if you think about hardware cache, the thing that they talk about in 61C, that is based on the address, and if the addresses are distinct, then the cache won't confuse them. If the addresses are the same, then the cache should confuse them because of the same address. Okay, good. Question in the back, yeah?
I think for the threads, the stacks that belong to each thread can crash up a little bit. They get too long.
Well, that's a different variant of the question that I was just answering. If your two threads are going, one of them is just, suppose it's computing Fibonacci of 5,298,000, and so it's just push, and it ends up overriding the stack, you end up with bad results. So the idea of having two threads in the same address space is there is no protection against that. Now, you can do a few things. So, for instance, we don't have the mechanism yet quite to talk about this, but you could imagine for the stack, you're never going to allocate all the memory for the stack until you need it anyway, and so you're going to put guard pages, they're called. And so if the stack starts growing, you sort of keep adding memory, and eventually there's a guard page that says, well, if you go past this, I'm going to put you into the debugger or fault your program or something because your thread has gone too far. So assuming that the threads are not malicious and trying to screw each other up, they will legitimately run into the guard page, and then you'll know something happened. But there's no way to enforce the threads will do the right thing. It's just that if you're using a good compiler and the right things are happening, in that instance, you will find out that the stack has grown too much. Was there another question down here? No. Good question. Yes? Yes, back to where I was. Here. Oh, so you're worried if the bracket's over here? Yeah. So this is an artistic license of what really happens, right? So in fact, the call to B is really or here you're talking about right here. So the call to C is some instructions, and the thing that gets put on the stack is the first instruction after the call to C, which would be then the return sequence stuff. So this is, you don't really put line numbers on the stack. It's just addresses. And so, once the compiler gets to compile this, what I'm calling the brace there is really the first instruction after the call to C. Good. But that's a good question. You called me on it. All right. Okay, so we return to there because that's what the stack says. And again, we're at a return. And here we look at a return. We return to B plus 1. Okay, and now we're also returning. So we return to A plus 2. And once again, we do Kube's printf, and we come out with 1 in this instance because temp is 1 in that stack frame. Okay? I should just change the slide to be KPF or something, Kube's printf. All right? And then the final thing we return, we get down to exit, and maybe the program exits. Okay, so there's your quick walk through what a stack looks like. Any questions? Good. Okay. So the stack has temporary results, permits recursive execution, can't do modern languages without it. The other thing that you need to know, and I'm going to enforce this soon, is you need to know that among other things, the way the stack is manipulated is part of the compiler and operating system contract. And we'll talk a little bit more about this. But basically, the compiler uses certain registers. Certain registers are called esaves. Certain registers are called ursaves. And the contract between the way the compiler produces object files and the way they're linked causes the stack to work in a certain way. And if you find a compiler that doesn't adhere to the rules, what you end up with is just bad non-functional code. So, all right. So let's take a brief break, and you guys can contemplate this amazing code that runs without threads and think about what's going to happen. But take a brief break. Welcome back, everybody. So, what happens with this code? We compute pi and we put the result in pi.text, and then we print out the class list and put that in class.text. So what's the behavior? Yes?
The computer never finishes computing pi.
That's right. So we never finish computing pi. We should just tell it it's 5, right? And then we never get to class list. So this is a good example of if you're trying to do this, which obviously everyone should be trying to do this at some point in their life, you can't get the second thing to run. So one thing we could do is come up with threads. So we could do something like this. Now, I'm going to put a disclaimer. We're going to talk about thread mechanisms kind of abstractly here without necessarily telling you exactly what happens in every operating system. What I want you to do is see what the operating systems need to do. Okay, so take this as we're not talking about an exact syntax of thread fork here. We're talking about a thread fork like what could be implemented in a lot of operating systems. And the idea of thread fork is just kind of like fork, that we're going to create a new thread in our current process. And so that means it's going to be in the same address space. It's going to run the function compute pi. And here's one of the arguments. This thread has one argument. This thread has one argument. So the rough idea, what we're talking about here is we're going to start two threads. One of them is going to be computing pi. The other one's going to be printing the class list. And what does thread fork do here? Well, it starts an independent thread running the given procedure. Now, there are pretty much all modern operating systems have nice, clean ways of creating threads. Okay, there was a time 20 years ago when threads were an add-on to library as a library. Those were called green threads. They didn't require kernel support. There was special behavior there. But, for instance, Linux has a native thread package that's pretty good, and they run in the kernel. So we're going to be thinking about that. That's kind of what we're thinking about, where this is a way to create a new thing that lives in a process address space and is a thread. Okay, and so in this case, the behavior here is you might actually see the class list, and it, in theory, should behave as if there's two separate CPUs, even if there's only one. Okay? Now, on a lot of modern machines, what will happen if you fork off threads is, depending on how your scheduler's configured, those two threads could actually use two separate cores if you've got a multi-core machine. If you have a single-core machine with no hyperthreads, then it'll go through this process that we just talked about a little bit ago of scheduling first one thread, then the next, then the next, and the next, back and forth. Okay? Now, all right? Fuchsia, cyan, fuchsia, cyan. I know you guys want me to say magenta, so I'll say magenta. Okay. Now, let's talk about two threads. This is particularly appropriate because this came up a little bit earlier. If we stop the program and examined it with the debugger, what would we see? Two sets of CPU registers, two sets of stacks. Questions might be, how do we position the stacks relative to each other? So it was great when we only had one thread, is we could have the stack grow down and the heap grow up. And yeah, if they ran into each other, that's, global Armageddon and all that sort of stuff. But, it's not really going to happen because you got a lot of memory in between. You can imagine if you got a lot of threads, now the idea of positioning the stacks gets a little tricky. Okay? And as I mentioned before, in principle, if one of the threads just goes nuts, it could overwrite the other stack. And there's not much you can do about it. But there are things that you can do to mostly help you debug. Like you can put in guard pages. So as this stack is growing down, it eventually hits a guard page which causes an exception and pops you into the debugger or dumps the state of the program or helps you figure out what's going on. Okay? But you could imagine the question, if I set a thread up, what's the maximum size of the stack that I want? Well, that's a question. And now suddenly, we have to have a better idea how our program's actually going to run so we could guess a good thread size. When there's only one thread per process, that's not an issue really, because you just let the stack grow down okay, and you don't really care. But if you have many threads, one of the things you might actually have to do is pick a thread's stack size for a thread. And most thread packages have a default stack size, okay, that's, big enough. What does that mean? Well, it depends. It means you're not making a really deeply recursive thing, right? If you make something really deeply recursive, other than being very cool to do in Scheme or whatever, it's going to run out of the stack, okay? And so just be aware that picking your stack size when you generate a thread, that's a real question here, okay? And what happens if the threads violate this? You end up with a very bad situation, because if the magenta thread overwrites the cyan thread stack, and then the cyan thread hits a return, it's going to return to somewhere, garbage, right? And I'm sure in several of your classes you've heard about various types of stack overwriting as a malicious remote access attack, where you manage to inject some code somewhere, and then you cause the stack to get upset just enough that the return jumps into the malicious code. Okay? So this is a real question. So how might you catch violations? So the guard pages is something I mentioned here. So here's some actual thread operations. So these are POSIX standard. There's a thread fork, which is a function and arguments, list of arguments. There's a thread yield, which is to relinquish the processor voluntarily. There's thread join, which is in the parent. You wait for a forked thread to exit, and then you return. Thread exit quits the thread and cleans it up and wakes up any joiner if there is one. So these are actual thread manipulation functions. And by the way, you'll get to play with them, okay, when we start getting into the labs. All right. So what is the dispatch loop on our single processor if we only have one? It looks conceptually like this. You run the thread for a while, you choose the next thread. You save the state of the CPU in the current thread control block, you load the new thread control block loop. Okay, and that's that thing I just showed you. You run the first thread for a while, then you run the second thread, then you run the third and come back, and in the meantime, you're always saving out the current state of the thread and loading the next state back. Okay? This is an infinite loop. All right? You boot the machine, it goes to the schedule loop. Okay? When you exit the schedule loop, you've probably either crashed or shut down your machine. Okay? So this is truly an infinite loop. So what does that say? Like, for instance, if I go to choose the next thread and there are no threads on the ready queue, what do I do? What do I do if there's no thread on the ready queue, so I have no new thread control block? What would be a good thing to do here? Suppose for a moment that there are no other processes. I heard that come out. That's good. Well, we had one thread we were running, and we're about to switch to another one, but there is no other one. What could we do? Anybody? Raise your hand. Yeah. Keep running the one we were doing. Yeah. Suppose that the one that we were running just exited, and we go to choose a new thread, and there's nothing to run. What happens? Yes? You compute pi. No. That's a good thought, though. Huh? So typically, modern operating systems often have what's called the idle thread. So if you actually look, the idle thread is the one that runs when nobody else can run. Okay? And all it does, in many cases, is it puts the CPU into a low power state to wait for the interrupt to wake up before it checks it again. Okay? But the idle thread is a real thread that's a kernel thread that basically does nothing until somebody's ready to run. Okay. All right. No good reason to exit the loop unless something really bad has just happened. All right. Question? No. So, how do we run a thread? Well, we load its state, registers, program counter, stack pointer into the CPU. Load its environment. That's the virtual memory space That's the address space, and jump to the PC. So how does the dispatcher get control back? So if you looked, see how I have run thread? Now, that's the dispatch loop. I need to exit run thread every now and then so I could choose another thread. Because if I don't do that and I just run thread forever, there's no way to switch off or get control back. Okay? And early operating systems, I mentioned this first lecture, and I'll mention this next time again. Early operating systems for users, for hobbyists, like early versions of Mac OS and early versions of Windows and a number of other ones, had voluntary exits from running. So every now and then you had to exit something called yield, which would give up the CPU voluntarily so the scheduler loop could choose the next thing to go. Okay, and the only way to make good code for those systems was you had to make sure you always ran yield frequently enough that everybody got to run. And it was true, I will tell you, that in the early days you'd load some code and you knew it was bad because all your windows froze. Why is that? Well, because the windows, you needed to do yield in your main program you were running so the windows could refresh. But if the main program didn't execute yield, then you were in trouble. Yeah, question.
Does that mean you didn't have to worry about locks?
Well, the problem is that there's a lot of other concurrency that still went on in device drivers and stuff. There were still interrupts, so there were some locks. That's an interesting question. Yes? Yeah, if you have multiple cores, this was relying entirely on yield was a pre-multiple core thing. Okay, because when you only have one core, then you could wait and then yield it. And that does act like a critical section that you don't have any parallelism in. But the moment you have two cores, now refusing to yield doesn't prevent problems with the other cores competing with you for the same data. So the real answer is if you have more than one core, you absolutely have to have a locking discipline. And we don't know about locking for another lecture or two. Go ahead.
Yeah, I guess it was like two cores that are trying to get the next thread to run that core.
Well, yeah, if you have two, if the run queue, or the ready queue is being shared by multiple cores, then the ready queue absolutely has to have a lock on it. Good. You guys are getting ahead of the game here. That's great. So how do we run a thread? So loaded state, load the environment, jump to the PC. How do we get back? So this question of how do we get back to the dispatcher is an interesting one. So there's a bunch of internal events where the thread returns voluntarily. So yield, I just told you, is one. Can anybody think of other internal events where the thread yields the processor that isn't explicitly through yield? What else? Yes. Say again? System calls. Awesome. Any I.O. that's going to block is essentially a yield. Or in fact, any I.O. at all is a yield. So when you go to make a system call, you're kind of saying, okay, go ahead and handle my system call, but also schedule somebody else to run. Okay? External events are ways in which the thread gets preempted. So what are good external events to preempt threads? Yes? Network packets, disk packets. What else? There's also one that even if there's no external I.O. coming in, what's a good external event from the scheduler standpoint? Yes? Yeah, timer. Great. So let's talk about internal events, things like blocking on I.O. So this is the act of relinquishing I.O. implicitly, yields a CPU. Waiting on a signal from another thread. Well, I'm waiting until I get a SIGINT or some other user 2 signal. That basically is like yielding. Or the thread executes yield. So here is an example of how you might compute pi on one of those early systems and still allow the windows to refresh. You'd say, well, true, compute the next digit, and then yield. Okay, and if you did that properly, then maybe your windows would keep working. Does anybody know why this is still bad? Well, the infinite loop thing, pi being an infinite number of digits. Okay. What else? The thing I'm explicitly wondering is, if I'm using this so that it'll work well, play well with others, why does this code still not play well with others even though it yields? Yes? Yeah, so the problem here is that compute next digit actually keeps getting longer and longer as the digits go out, depending on how, because you're expanding in a series and computing, you need to compute more and more series parts of the series in order to get the next digit. And so this compute next digit gets longer and longer and longer as time goes on. And so it would start out very responsive, and then compute next digit would take longer and longer and longer and longer. Okay. So here's a stack for yielding a thread. So I want to show you, here's the stack. This is the user's portion of the stack. It's computing pi. It has yield. We trap to the operating system. So a system call is a synchronous trap with a number associated with it. So yield's a good example. And we switch out to the kernel stack, because we can't trust the user stack, which is we put kernel yield on the stack. That's sort of the yield frame. Then we run new thread, and we switch. Okay, and how do we run a new thread? So we say here we pick the new thread, we switch the current thread for the new thread, we do some housekeeping like keeping track of how long we've been running and how many cache misses and whatever, and then we're done running the new thread. Okay, but what's a little interesting here is, what does this mean, switch? Okay, so how does the dispatcher switch to a new thread? Okay, and this is going to be kind of our last topic, and I'm going to leave it with you to sort of blow your mind a little, and then we'll get back to it next time. But the dispatcher switches by saving anything the next thread might trash, program counter, register, stack pointer, in the stack, and then it's going to switch, and here's what the stacks look like. So here's two procedures. A calls B, and B says while true yield. Okay, and I'm just giving you this so that there's two stack frames here. And suppose we have two threads, S and T. So thread S has an A stack frame calls B, which calls yield, which calls run new thread in the kernel, which calls switch, which switches to the other stack frame, which exits run new thread, which exits yield, which exits B, and then runs yield again, run new thread, switch, which goes back to the other stack frame. Okay, so look at this code for a moment. This is a little weird. What you see here is the reason thread S and T run together at the same time is because when we go down, we save, we have a stack frame for each one of them, including the kernel portion of the stack. We get into run new thread. It gets into switch. It switches all the stack pointers, the stack pointer, to be over here, so that then when we return from switch and return from run new thread, we end up in a different thread than we started. Okay? Now, let me just show you what switch looks like sometimes, right? So switch, written in assembly language typically, says my thread control block, I take all the actual registers, I throw them in the current thread control block, I load the new thread control block, including the return PC for the new thread, and then I execute return in assembly language. So this is representative assembly language. But when we're done, that down return actually ends up returning to a different stack frame and thread than the green one entered. So we enter this procedure in green, we exit in red, and that's why we do thread S through T and back again. Okay. All right. Questions? So, interesting questions. What if you make a mistake in implementing switch? Suppose you forgot to save and restore register 32. What's going to happen here is you're going to get weird intermittent failures where just only when you switched does the fact that register 32 was wrong cause a problem, and maybe register 32 is not always in use, and so you don't always notice it, and so you get the wrong result very intermittently, and it's very hard to debug. So of all the routines in your kernel that you absolutely have to have absolutely correct is this one. Because if there's anything wrong with this, you're going to get weird, non-debuggable problems, and it's just going to be bad. Okay, this is really bad. All right. So, can you devise an exhaustive test to test the switch code? No, there's too many combinations and interleavings. And this cautionary tale is pretty funny. So, Digital Equipment Corporation built the Topaz kernel. It wasn't funny for them, by the way. And they they thought switch was so important to them that they were going to save an extra instruction that they carefully documented so that it only works as long as the kernel size was less than 1 megabyte. This extra instruction didn't have to be used, and this was going to be faster by one instruction. And what happened? Time passed. People forgot. They added features to the kernel. The kernel got bigger. And very weird behavior started happening one day when somebody put some small thing into the kernel and relinked it, and all of a sudden everything broke. And the reason it broke was because of this assumption in switch people forgot about. Okay, so this is a great example of designing something for simplicity and generality, and perhaps saving one instruction is not always worth the trouble. All right, so in conclusion, we talked about sockets again, which is an extraction for one end of a network I/O. Processes have two parts, threads for concurrency, address spaces for protection. And we talked about concurrency being accomplished by multiplexing CPU time, unloading current thread, loading the new thread, and switching. Context switching can be voluntary or involuntary, and we're going to expand on this next time. So have a great rest of your Tuesday. May the net force be with you. F equals MA, rules the universe. And we'll see you on Thursday.